so that it can continue from where it left off in its next time slice. To do this, the contents of various CPU registers are saved to its process control block. Each process has its own process control block. To do this, the contents of various registers include the program counter to its process control block, the memory address register, each process, and the memory data register control block. To do this, the contents of the next process in line takes control of the CPU and its previous state is restored. The memory address register, each process, and this is called context switching. To do this, the context switching takes about 10 microseconds, which of course is an overhead. This state is restored. 10 microseconds is a relatively short time compared to the length of a time slice. To do this, the context switching takes about 10 microseconds, which of course is an overhead. This state is restored. 10 microseconds is a relatively short time compared to the length of a time slice. To do this, a blocked process gets the services of the input-output device that it was waiting for an overhead. It can be placed back into the ready queue by the low-level scheduler for another burst on the CPU slice. And it is once again time sliced along with the other processors that it was waiting for an overhead. It can be placed back into the ready queue by the low-level processors are coming and going all the time. In fact, the operating system consists of several processors which must run continuously to keep the machine working properly. Back into the ready queue by the low-level processors are coming and going all the time. In fact, the operating system consists of several processors which must run continuously to keep the machine working properly. Back into the ready queue by the low-level processors are coming and going all the time. In fact, to summarize them, consists of there are never no process continuously to keep the machine working properly. Back into the ready queue by the low-level processors are coming and going all the time. In fact, to summarize them, consists of there are never no process continuously to keep the machine working properly. Back into the ready queue by the low-level processors are coming and going all the time. In fact, to summarize them, consists of there are never no process continuously to keep the machine working properly. Back into the ready queue by the low-level. This means that queues can be implemented as linked lists or as binary trees. In fact, these aren't first-in, first-out queues. They are usually priority queues, in which case the highest priority item is dequeued first. Another part of the system, known as the medium-level scheduler, might move a blocked process temporarily to secondary storage. The scheduling algorithm depends very much on the operating system. In fact, there might be multiple ready queues for processes of different priorities. Windows uses a round-robin scheduling system with multi-level feedback queues. This means that processors can move between queues depending on how long they've been waiting. And finally, a high priority interrupt will pause normal scheduling. In a simple scheduling system, there is a ready queue and a blocked queue. Part of the system known as the high-level scheduler is responsible for admitting new processes to the system. The high-level scheduler is sometimes referred to as the admissions scheduler and sometimes as the long-term scheduler. Another part of the system, known as the low-level scheduler, is responsible for taking a process from the ready queue and moving it into a running state, allowing other processes in the queue to advance. All the while, new processes are being admitted to the system. When a process finishes, it can exit the system. If a process cannot continue because it is waiting for the services of an input-output device, it is moved by the low-level scheduler into the blocked queue. In a round-robin scheduling system, processes are allocated equal time slices. When a processor's time slice ends, the low-level scheduler will move it back into the ready queue, allowing another process to take its place in the CPU. Time slices are between 10 and 100 milliseconds long, depending on the operating system. This is a relatively long time when you consider the rate of clock cycles. In a 2.6 GHz processor, the clock cycles 2,600,000,000 times a second, which means that a single time slice lasting 100 milliseconds is 26 million clock cycles, enough to execute more than just a few instructions. When a processor's time slice ends, its state must be saved so that it can continue from where it left off in its next time slice.
Hello. Are you able to listen me?
Another natural question can be, can processes interact? And the simple answer to this is yes. An operating system must provide mechanisms to allow processes to interact with one another. And today, in fact, more and more of the applications we see are actually structured as multiple processes. So these multiple processes have to be able to interact to contribute to a common goal of a more complex multi-process application. For instance, here's an example of a web application consisting of two processes on the same machine. The first one is the web server, the front end that accepts the customer requests. And the second one is the back end, the database that stores customer profiles and other information. This is a very common case in many enterprise and web applications. So how may these processes interact?